One of my biggest concerns I have with the way this material is taught is that very little attention seems to be paid to numerical solutions or computer simulations of these problems. And of course, for all other than the most simple problems anyway, a computer is required to give us an approximate solution. So I thought I would start off just by looking at the simple harmonic oscillator. We have a mass spring damper system here, drawn on the right. And the equation of motion, as we know, is mx double dot plus cx dot plus kx equals f of t, where f of t is this external force. And we'll call that equation number 1. And the way we go about solving this on a computer numerically is we would like to write this equation of motion in a form that's known as state space form, sometimes just called state form. So we want to rewrite equation 1 in state space form. So rewrite in state space form. And again, the idea is we want to take the second order differential equation and write it as a first order differential equation. And the way we do that is we define a vector y. We say let some vector y equal x, how do I want to do this, x dot x. So I'm defining a vector where I take the coordinates x dot, the velocity, and x, the displacement. I stack it in a vector, and I'm calling that vector y. And this would be equation 2. And what this implies, if I take the derivative, the first derivative of the vector y dot can be written as x double dot and x dot. And that would be equation 3. So I'm going to rewrite 1 as, let me just write it and then we can talk about it, m 0, 0, 1 times x double dot x dot plus, got a matrix here that is C, K, minus 1 and 0. And that is equal, well, left out the vector, x dot x, and that's equal to f of t and 0. We'll call this equation 4. All right, so what have I done in equation 4? I've written 2 separate equations. I'll put a dotted line here, you can see that. The top half is just my original equation of motion. Why? Because if I multiply that out, that gives me equation 1, namely m times x double dot plus c times x dot plus k times x equals f of t. I could have instead written the c here and made this element 0. It would have made no difference. I just chose to do it this way arbitrarily. Then the second equation in the system of equations merely says that x dot minus x dot equals 0. 1 times x dot is equal to x dot, minus 1 times x dot is minus x dot, and that's equal to 0. And the second equation is known as a constraint equation because it's fundamentally saying that the second element of this vector is equal to the first element of that vector. It's constraining the system of equations in that manner. So it might seem like this is no big deal. All we've done is we've replaced equation 1 with equation 4, where we have twice as many equations because we've added this constraint equation. But now if we substitute equation 2 and 3 into 4, we can rewrite this as, I'm just going to call this vector A, this matrix A, and I'm going to call this matrix B. And then I can rewrite this as some matrix A times the vector y dot plus some matrix B times the vector y is equal to, and I'm going to call this capital F. It's an f of t, but we'll just call it f for now, where this is f here. Well, I should write it as a vector, I suppose. This is vector F. So vector F is just the stacked force vector, which is F of t in the first position and 0 in the second. All right, so what have I done? I've now taken equation 1 and I've written it as equation 5, where, true, I've got a system of equations, but the derivative is only first order. We look at the vector y. It's a first order differential equation now. So I've taken one single second order differential equation and I've traded it for two first order differential equations. There are two equations in the system. Okay, now I proceed by discretizing equation, well, let me just rewrite equation 5 like this. I can solve for y dot by just moving everything over to the other side. So what does that give me? I've got f minus b times y. And I'm going to pre-multiply this by A inverse. So what did I do? I moved the by to the other side, which is why I've subtracted it, and then I pre-multiplied by A inverse. Why did I not divide? Well, because we're dealing with matrices here. You don't really divide by a matrix. What we do is we multiply by its inverse. And in this case, we're pre-multiplying because in matrix multiplication, we know that order is important. All right. So equation 6 represents a first-order differential equation in y. And we can discretize this, and we can use a computer to do a time-stepping solution as follows. So we want to discretize 6. Discretize 6. And we do that by taking this y dot and writing it in discrete form as delta y, the difference in y, divided by delta t, the difference in time. So the difference in y would be y at time t plus 1 minus y at some time t divided by the difference in time, which is delta t. And that is equal to what we have above, A inverse times the vector f minus b times y. All right, and now I'm just going to rewrite this in terms of yt plus 1 and take everything else to the other side. So this implies that the vector y at time t plus 1 is equal to, I'll write it this way, delta, yeah, let me write it this way. It's y of t plus delta t times A inverse times f minus by. All right, and what this is telling me, and by the way, this y is y at t now. This y up above here is y at time t. So everything on the right-hand side of the equation depends on the state y at time t. Y is known as the state. And I can find y at some time step, the next time step t plus 1, by only having knowledge of y at time t. This is called an explicit integrator. Let me write that here. So explicit numerical integrator. And all we need to do this time marching or time stepping solution is we need an initial value. And we know what the initial conditions or initial value is. Let me write IC. The initial condition is that y at time 0 is equal to x dot 0 x 0. So in other words, by being given x dot, the velocity, and the displacement x at time 0, we know what the initial state vector is at time 0. And by using that, we can do a time-stepping solution using a computer to advance the solution for every next time step. Now, might be a little bit wordy right now, and what I'm going to do in the second part of this video is implement this in a Python code, and so you can see in no uncertain terms exactly how all of this works. There'll be no guesswork. But fundamentally, this equation here, which we're calling equation 7, is what we're going to implement in a computer code to show what y is, the state, as a function of time. From there, we can find the displacement x and the velocity x dot. And we'll call this initial condition 8. Okay. Before we start, I want to show you one real quick check that needs to be discussed, just in terms of understanding how good is my numerical integrator, and more importantly, what is the delta t that I use? How big or how small a time step do I want to use? If my time step is too big, I'm going to lose accuracy. And if my time step is too small, then it's going to take a really long time to come up with a solution. So we'd like to find a happy medium, but we need some way of gauging, are we accurate enough or not? So turning the page, we'd like to test the numerical integrator. And what we do here is we apply the conservation of energy. So we know that at any given time, the system kinetic and potential energy must be the same in the case of the free vibration problem. In other words, in the absence of any external work being performed on the system, the total energy, the sum of the kinetic and potential energies, must remain constant. So we call the potential energy, or the kinetic energy rather, T is equal to 1/2 times mass little m times its velocity x dot squared. We'll call that equation 9. And we know that the potential energy is equal to 1/2 times k times x squared, which is the potential of the spring. And then we know for the free vibration problem, let me write that out, for free vibrations, that T plus V is equal to constant. So typically we set the system in motion using one of the initial conditions being non-zero. Either there's a displacement, or there's a velocity initially, or both, in which case it has kinetic and or potential energy. And whatever that initial total energy is, kinetic plus potential energy, should be preserved. So we'll call this a consistency check, and we will add this in the next video when I implement this in Python. So I'm going to cut the video off at this point because I don't want it to run too long. We'll make this a 2-part video, and in the second part I'm going to take this theory that we've presented here, and I'm going to show you how to implement it in a computer simulation, or a numerical solution is another way of calling it, where we take this the system and we actually do a time marching solution using a computer and simulate it that way. Anyway, that's it for this video. I hope you found something useful in it. If you did, please go ahead and leave us some comments below. I'd love to hear from you, or give it a thumbs up so that others can watch it too. Better still, go ahead and subscribe to our channel, and you'll be informed of any future video releases. Thank you for watching, and I'll catch up with you in the next video.